Welcome to class, everybody. Hopefully this time we're actually live. I was already going deep in the lecture because I saw people responding on Twitch and I didn't realize that the connection wasn't on. So back up YouTube Live. This actually was the first time that I ever streamed for class was on YouTube Live. So we actually moved away from YouTube Live because we had a lot of technical issues. So hopefully that's not the case anymore. I can see it's still the chat. Let me go ahead and put that somewhere where it's easier for me to see. I actually see the video myself, so hopefully it doesn't actually lower the bitrate. But yeah, the one advantage of the YouTube live system is that when the stream finishes, the video is already on YouTube. I may still upload it again in higher definition if I see that the quality is not the best. I should start recording for that then. Hold on, so here we go. So I am recording locally now. So if something does happen to the video, I will upload it by hand. So great. Let's go ahead and there we go. Okay, cool. So welcome to class. Today we're going to talk about binary search and other sorting algorithms, and depending on how long that takes, we may talk about structs a little bit. If not, we could also end class early. We will see how the internet does. So yeah. Oh, okay. So this was actually what I started talking about before the issues. So this is the code from last class, right? The bubble sort. And one of the things that I told you, but I didn't actually get to show you, is that the code as it is now is basically, if we compile and run it, you know, we got your numbers going up, right? Counting up, which we call a ascending order, or better yet, a non-descending order, right? Because the reason why we like that name is because it actually accounts for duplicates. So what if we want to reverse that? What if we want to sort in a non-ascending order, which would be a descending order, right? So we want to count down, basically. What do we want to go from 11 to 0 potentially? Well, I told you briefly that all you got to do is switch a sign. And that is the case, that all you got to do is switch a sign. But where and what is that you have to switch that sign? It's actually in your if statement. So the way this works is basically that when the number on the right is less than the number on the left, that means those two are out of order. So that's why you swap them so that now the bigger number is on the right. That way, you know, you have this increasing order, right? That's the decision that makes you sort this, you know, if you boil it down to the tiny, tiny step. Cool. So if we want to sort in the other direction, then what we want is we want the right number to actually be smaller than the left number, because then it's going to be going down. And so that means that the right has to be less than the left. We don't do anything. But if the right is bigger than the left, that means they're swapped. So that means we have to swap. So what all this boils down to is in your if statement, you're going to switch that less than sign or greater than sign if you did it this way. Because remember, this one also works. These two are the same thing. I just flip them around, but I also flip the sign. It's all, you can think of it like the little eating sign. It's always eating the number on the left side. Here, this is the left number, so it's eating it this way. Here, this is the left number, so it's eating it this way. And it's going away from the right number, right? So all we're going to do to fix this is just flip the sign. Whether you have it in this method or this method, just flip the sign, but don't flip the indices. Like that. Save your code. Recompile. And now you can see that it is going from the highest number to the smallest number. And so that's all there's to it. Whenever you got to change how you're sorting or by what you're sorting, all you got to do is deal usually with that comparison piece of the code. And that's pretty much it. So I just thought I'd show you that just since we didn't see it. But ultimately, it's more important that you understand why changing that tiny sign completely changes the way this sorts. And so that's the most important part. And that's because that's how you're deciding when to swap and when not to swap. And if you never swap, then nothing would get sorted, of course. So really, when you're swapping and how you're swapping is what really makes an algorithm fast or slow when it comes to comparison-based sorting algorithms, because you only want to swap the least amount of times because each swap takes time. The two things that are going to make your algorithm slow or fast are how many numbers you got to look at and compare. So how many times do you need to compare two numbers? And then after you do that comparison, how many swaps you actually have to make. And the combination of both of those measurements will tell you how fast your sort algorithm is. And so ultimately, bubble sort is slow because you have both a lot of swapping going on, but more importantly, you have a lot of comparisons. And that's really what kills it. We did try to optimize it a little bit by removing some of the unnecessary comparisons, and we can't really decrease the number of swaps. That's just the way it has to be with that. There's no way to decrease that without changing the actual algorithm itself. So lowering the comparisons helps a lot, because that's really what takes a lot of time. You gotta pull those two values from memory, look at them, decide if one is bigger than the other one, and then do your swap. And that pulling and looking does take quite a while of time, especially when you're thinking about billions of numbers potentially, if it's a big list that you're sorting. So that's bubble sort for you. But okay, so what is the point of sorting something? As I said last time, one of the advantages of sorting data and basically organizing the data is so that you can retrieve information faster. If I gave you a dictionary and I told you to look up a word in the dictionary, you can find it relatively quickly because the dictionary is alphabetical. So you have a system, and we can talk about that in a second, but it's easy to find, right? Imagine that I gave you a book, just any book, not necessarily a dictionary, and I told you to find the word potato in the book. How do you do it if it's just a normal book? I mean, obviously if the book is a subject related to potatoes, that makes it easier, but if you're reading like, I don't know, Tom Sawyer or some random book, that's very hard to do because there's no certain order to the text that allows you to make it easy to search something. The text is potentially in a special order, I guess, because it's actually meaningful text. I mean, there's sentences and things like that. But for your purposes of searching, it may as well just be a spaghetti soup, because there's no easy way unless you just literally scan every single word, right? Whereas with the dictionary, because it's alphabetical, you know where to look and you can kind of skip there rather quickly. And so the advantages of sorting in data is the same reason why we have a dictionary that's alphabetical and not just has all words randomly stored in there in any order, because it makes searching faster. And of course, the dictionary, the main goal of a dictionary is for you to be able to look up things fast. Whereas when you're reading something, the idea is not to look things up fast, but simply to read it, right? And to understand it, and for it to make sense in English. So different purposes require different algorithms, right? And so now that we've learned how to sort something, and of course it's not the most efficient way, but we have learned a way, we can actually prepare something in a sort of dictionary-esque style of ordering, right? And so now let's talk about why searching through a dictionary is faster, because I'm hand waving and I'm saying, well, yeah, it is faster, but like, what makes it faster? Like, in reality, why? Well, it turns out that even when we are looking through a dictionary, we are somewhat performing what is known as binary search. It's not the most efficient version, but it's somewhat of a rudimentary version of binary search. What happens is as follows, and maybe I should have had a book with me to kind of show you that, since I usually do that when I'm actually teaching in person. Oh, snap. Yes, I have a book, so stand by. Let me see if I can reach the book. Hold on a second. Let's yes, okay, so give me a second, guys. All right, cool. So here we got a book in the fresh. This is Computer Organization and Architecture. It's a class I'm teaching summer 3, so I have to kind of start refreshing the material. So yeah, it's a pretty thick book, right? However, suppose that I want to find a specific page on the book. Okay, I want to find page. I want to see if, I mean, spoiler alert, it probably exists, but I want to see if and what contains page, I don't know, there's a lot of pages here, so I'm going to go with page 455. Okay, that's my goal, to get to page 455. All right, I'm going to open the book at some spot, and I got page 321. That would have been scary if I got 455 right there and then. That has happened before, actually. So, okay, cool. So, because I know this is page 321, what can I say about all of these pages? What I can say is that the page 451 is not found in any of these pages. Why? Because if it was found in those pages, then the number here would be smaller than 455, right? But it's not, because this page is 321. And so I know that if such a page is in the book, it's in here, right? Okay, so I just have this big chunk of pages here, and I know it's about 100 pages, so I kind of just open it in the next spot here, and I don't let go over here, and I take a look. All right, I'm at page 647, so I'm way over. But that does mean that all of these pages over here are bigger than 451, so I can get rid of those. So I know that the page that I'm interested in is in here, or at least it may be. You know, it might be missing the page in the book. It's very possible, you know. But the point is that if it exists, because we know it's in order, it's gotta be in here. Now, as a human, I'm like, okay, this is 600 and this is 300, so it's more than likely gonna be kind of on this side. So I'm kind of gonna go here and look, and I get a page 405. So that's pretty close. So that means that these set of pages is not where it is, and it's still within this section. Okay, so I'm kind of getting close now. About 50 pages, so I just kind of grab a smaller chunk of pages, and I go like this, and it says 438, so it means I gotta go a little further. At this point, maybe I just go page by page, and this is 449, and then I just need one more page, and then get to 451, right? I can do that because I actually happen to know that most books don't skip pages, right? But that may not be the case when you have data. Yawning dog. That may not be the case when you have a list of numbers, because they may not have all numbers inclusive, right? They may be like 1, 5, 10. Once it's sorted, it might look like what we had. So like this. You know, we got 0, we got a bunch of 1, so there's repeats. Then we got a 3, so there's no 2. Then from 5 it goes to 10. So it's not necessarily a continuous flow of numbers like a normal book is. So a book is a sort of an even easier example. But what I'm about to show you will work whether or not you're using numbers that are like continuous or they skip. So anyways, finally get to 451. I'm actually curious to see what is in this page. Shift and rotate operations. Oh, logical right shift. Actually, we should talk about shifting at some point. Bit shifting. X4. Interesting. Okay, so yeah, that's what was in this page, right? So how many pages did I have to look at to get there? Well, you can rewind the video and tell me in the comments, I guess. But my guess is I looked at about 5 pages, right? I did about 5 splits before I got to the final thing, maybe 6. Okay, 6 to get to that page. Now imagine that the whole thing was out of order. I have to scramble every single page, and I couldn't skip it, because if it's out of order, then who knows, right? So even if it's in order, if I don't use some smart method, you know, if I give you this and you want to get to page 451 and you just open it on like the first page and you just go page by page, why would you do that when you know that the page is way beyond, right? So we know that we should just kind of skip, you know, 300, 387, 433, 457, I overshot, 465, 461, 457, 449, so I went over too far. 451 again, okay? So again, that's how we normally do a book. Nobody really taught us that. We just kind of picked it up, I suppose. I don't think I ever taught me how to look in the book, right? So, why am I showing you this? Well, this is basically how binary search works. The idea of binary search is you want to save time in searching when you know that the data is in order by applying our divide and conquer systems. We basically have a list of numbers, and we split it right in the middle of the numbers. And we look at the left side and the right side of that split. And we look at where it got split. And just like in the book, if we open it in the middle and we got past the page because we got to page 600 and we were looking for page 400, that means that we can discard one side entirely from searching. And now, even if at that point you switch to just doing linear search, you cut the number of pages that you have to look at by half. Because if you got 100 pages and you're looking for one page, let's say you're looking for page 48, and you look in the middle of the book and it turns out it's about page 50, you know that you don't need to look at page 50 to 100 because the page you're looking for is in the first half of the book. So you've already cut the number of pages you have to look at by half. But we don't stop there. We can keep doing the same logic again and again to cut it even farther. So from 50 pages, you can cut it again by half. And now you're only looking at 25 pages. And then by half again. Then at 12, then at 6, then at 3, then at 2 potentially. And you probably at that point have found the page. Or you might need to do one more page forward and back. So you're thinking, okay, but if it's page 48 and I put it at page 50, why don't I just go back one page? Yes, that will work if and only if your data basically includes whole numbers. But now let's give an example where while the pages are in order, they skip a bunch of pages. So you may have page 1, then the next page may be page 100. And then pages 100 to 200, you have every single digit. And then page 200 to 300, you have yet again just one page. Like maybe I'm saying maybe like every 10 pages. So like 210, 220, 230, 240, 250, right? And so if you have such a situation, you look at the middle of that index, and that middle of that list is going to be approximately about page 100, even though there's 300 pages in the book. Because there's 100 pages early on, and there's 100 pages later on, and there's basically no pages in the middle of the book. And so we want to make sure we account for that and not just try to cut corners like we can in the book when we know that all pages are there. And so that's kind of what we're going to do. So let's go ahead and take a look at sort of a drawn example of how we're going to do this. Everything good still on the stream? I don't see any comments, so that must be a good sign. I will change all the title and the description after the stream ends, so that it's more descriptive for people that come later. Okay, cool, nice. All right, so let's go ahead and throw in some numbers here in a sorted manner. So let's say we had random numbers and then we sorted them. So we have the numbers 1, 5, 20, 80, 100, 101, 102, 190, and then 181. Okay, so this is the list that we are working with. Okay, that did not turn out to be a rectangle. Let's try that again. Wow, okay. I guess I can't draw rectangles today. There we go. That actually does not look anything like I wanted it to, but I guess I have to maybe straighten out my numbers first, but okay. So we have this, and more importantly, we have it stored on my computer on a vector or an array, which means that each of these have indices. Like such. Okay? And so now we want to be able to search through this. Of course, suppose that we're looking for the number 150. Okay? The most naive and simple way, which is the way that I showed you before, is you just go one by one. So you look at this, you look at this, you look at this, you look at this, and you look through the whole thing. And if you find 150, you can return like, yay, I found it, or better yet, you can return the location of it, so the index. However, in the most naive way, you're actually going to check the whole thing because you disregard the fact that it's sorted. Okay? That's the most easy, naive way. A better way to do it, that is still relatively simple, and you don't have to change a lot, you actually just have to have kind of like a break statement, is let's say you're searching for the number 150 again. But because you know it's sorted this time, after you get to the 102, you keep searching, you get to the 190, but then you're like, oh, well, if it's sorted, I'm looking for 150, and I got to 190, it means that the number can't be there, because otherwise it would have shown up already. Okay, it's an elegant solution. It's not necessarily going to be much faster, although in the case where the data is found, you will definitely save a little bit of time, because say that the number you're looking for was 1. You find it in the beginning and then you don't need to keep going, right? So that would be a nice case. The worst case, of course, is if the number you're looking for is bigger than the last number in your list, in which case it won't make a difference in which method you're using. Okay, so neither of those is really kind of taking advantage of the fact that the list is sorted, like in a meaningful way. Binary search will. So how binary search is going to work is we are going to, again, let's say we're looking for, let's look for a number that's here. Let's look for the number 190, okay? And so what we do is we first look in the middle of the list. Now, what is the middle index of this list? That happens to be the number 100. So that's index 4. So this is the middle of the list, okay? So we look, so basically the first thing we're going to do is we let's put a little square here, what we're looking for. It really doesn't like drawing squares, so like it just tries its hardest to just not make it a real square, but okay. It's look like a SIM card. But okay, so the number we're looking for is 190. Okay, obviously we are humans, we see that it's there already, but you know, that's because it's 10 numbers, okay? Multiply this times a billion numbers and now try looking for it, right? Okay, so we're looking for 190. So the first thing we're gonna do is we're gonna find the size of our list here. What is the size of the list? The size of the list is 9, right? Remember, the range is 0 to 8, but there's actually 9 items in our list. So what we're gonna do is we're gonna take the 9 and we're gonna divide it by 2 so that we can find the middle of the list. So 9 divided by 2 is equal to what? 4.5. However, remember with your integer division, that just ends up being a 4. And that actually, we can take advantage of that because we don't have an index called 4.5. We would either have to look at 5 or 4. But if we just take advantage of the fact that integer division in C++ just removes decimal, then we can be consistent about which side we end up taking. So we're always going to the rounding down side per se. Either one would actually work, but you know, why change the wheel if C++ lets us go one way? So 4. And so we get to the 100, right? And so from there, we are going to look at what is an index 4, which is 100, and we're going to compare it to what we currently have that we're looking for. So we're looking for a 190, and we found 100. It turns out that, surprise, surprise, 190 is bigger than 100, right? So what does that mean? That means that if our item is found in this list, and it may or may not be, we don't know that yet, it's going to be on this side of the list. Because 190 is greater than index 4, which has 100. So it's impossible for our item to be found in either the left side, and of course we have actually checked already that it's not here, because we're literally looking at this one spot and we're saying, well, I guess the first thing that we want to do is see if we got lucky, right? The first thing we want to do, I suppose, when we look at index 4 is like, hey, is this the number we're looking for? Like, did we just get lucky? Of course it's not, but then we can see, well, okay, it's not. But is it bigger or smaller than the number we're looking for? In this case, it's smaller. And then we're like, okay, because it's smaller, we need to go and look on the bigger side, right? And this, of course, is because this is an ascending order list. Yet again, if this whole thing was descending, you would flip the logic with a greater than sign to a less than sign and that kind of thing. But anyways, so that's what we're gonna do. And so here's some loud noises outside. So I don't know what that was. But okay, I think it was probably a car or something. But anyways, sorry about that. Okay, so bring it back. Okay, so we looked at 100. it's smaller than the number, so we're gonna look at the right side, okay? But now we're not just gonna linearly look. We're gonna do the exact same thing. We're gonna take the remainder list and just think of that as the entire list that we have. So we're gonna consider this to be our entire list. So let me go ahead and kind of grab that and bring it down here. I do wonder what that noise was. Okay, so this is what we're looking at right now. There we go, okay? And so, yet again, what we're gonna do is we are gonna take the range of numbers from 5 to 8 and find the middle of that. There are many ways to do this. The best way to do it is just to add them together and then divide them by 2, or take the range and divide that range by 2. So you could do something like 8 minus 5 divided by 2, and then basically you add that to the 5. So 5 plus whatever this is. So what is that equal to? Well, 8 minus 5 is 3, and then 3 divided by 2 is actually just going to be 1 because of the modular stuff. So ultimately, we're just basically doing 5 plus 1, which is equal to 6. So this is a situation that's going to happen in a scenario where things are even size. In the odd size, it's very nice and easy to get a middle, right? But when you got an even number, technically, this could be the middle or this could be the middle. You don't want to just look there. You always want to land on a number, okay? And because you always want to land on a number, then you got to just decide. But yet again, if you just go with whatever the division here gives you, because really, I mean, if you do the exact division here, it's 1.5. So really the middle of this is 6.5, which is true technically. 6.5 would be like right in the middle, but that's not an index, right? And so again, you got to stick with one side. Just be consistent about this. And the way you can be consistent is by just doing the integer division, which rounds down, as I said. So, okay. We went ahead and did that, and we've landed here. Okay? From there, we're going to do the same thing that we did before. We're going to look at what we're looking for, which is the 190. And we're going to compare that with index 6. We're going to say, is 190 bigger than, equal to, or less than index 6's contents, which is 102? I guess, again, we want to ask ourselves, did we get lucky? Did we land at the actual number we were looking for? The answer is no. That's fine. Okay. But the number, the 190 is bigger. So we have already eliminated, potentially from this, the 101. Our number is not there for sure. And of course, it's not where we just landed. So that kind of leaves us only with 2 numbers, right? And so, yet again, we're going to, even though there's only 2 numbers left, this is all theoretical, right? This could be big numbers or this could be small numbers. So we're going to do the same thing we did with the remainder of the list. So we're going to go ahead and take the last 2 numbers here and do the same thing, okay? So yet again, we can do a little formula, which I guess I'll write with variable names. So we can say the right minus the left divided by 2 and then the 5 is going to be the, I wrote that backwards, didn't I? Yeah, I wrote that backwards, my bad. There we go. So we take the left, which of course could be like a 5, and then we take the right, which of course could be, Did I write that? I did have it right. And I flipped, because the right is, yeah, damn it. Sorry. Okay, I think this one's the good one, guys. So, yes. Okay, because the right side is the bigger one, and then the left side is the smaller one. And so the 8 is the bigger number, and the 5 is the smaller one. So, yes. It's a lot easier to think about this than to actually write it with right and left, because I always get those mixed up for some reason. But, okay. So, really, what this actually kind of gets converted to is basically 8 minus 7 here. So, 8 minus 7 divided by 2. And this whole thing, 7 there. Of course, this is a lot of mumbo jumbo for essentially what's going to be 0, I believe, because 8 minus 7 is 1, and then 1 divided by 2 is actually 0, because that's actually, it's 0.5, but yet again the 0.5 gets dropped, so this turns out to be 0, and so basically you're doing 7 minus 0, which is just 7, right? So a lot of work for just a 0. But it's okay. What that means is we are going to be looking at 190. At that point, we're going to check whether we've got lucky, whether the number is bigger than that or smaller than that. Now, in this case, you can see that there's basically nothing. So if the number was potentially smaller than 190, because this list is empty here, there's nothing beyond that we haven't checked, that is going to tell us that we haven't found what we're looking for. On the other hand, if we were to look over here, beyond that, we will do the same thing one more time. Of course, we could use shortcuts and say the size of list, the remainder list is of size 1. We might as well just check it now. You could do that as well. But again, you don't have to if you're doing the most simplest version of this. However, in our special case, we were looking for 190, which is what is found here. At that point, we are like, you know, we found it. And of course, we can return what index we found it at, because that might be very useful, which is index 7. Okay, that's the 8th item in our list, technically, because we start counting from 0. So, yeah. Oh, I can see the delay from this. But yeah, so that's basically how the algorithm works. And it's a little bit complicated versus like bubble sort or something like that, but not too much. It's actually harder to describe it than when you look at the code, though. The code looks simple, and yet at the same time it's kind of weird. Like you're like, huh, that does what we just said, but it does. And you know, it's I guess it's one of the first again algorithms that you're learning. And so, how fast is this? Like, how fast is this compared to like just linear search? Well, think about it. Every time that you are doing this, you're dividing the number of items you have to check by half. So you're doing the half of the half of the half of the half of the half. Turns out that if you graph this, it's basically a logarithmic curve. And so, on average, the amount of comparisons that you have to do to find whether the item you're looking for is there or not, and of course, if it's there, what the index is, it takes log of n times. Log base 2, technically. So what does that mean? Well, if your n is equal to 8, and n stands for the size of the list, so the number of items in your list that you're looking for. So in this case, it's 9, but let's just go with 8 because it makes the logs easy. If we had 8 items in our list, on average here, we're going to be basically doing log to 8, which gets simplified to 3, right? Because 2 to the 3rd power is equal to 8. If you don't remember logarithms, basically what the log says is 2 to what power is equal to 8. And that's the answer to basically saying log 2 of 8. In fact, I suppose I could write this like this in math. Be weird, but yes, that's basically what we're saying. The number here is going to be equal to that. Of course, there's a math property that says that you can just bring it down. If you have a power to the same log, then you can bring that down. But that's 302 world, not our world yet. But yes, you do use math and see computer science. Surprise, surprise. But yeah, so basically that's what logs are, and essentially this tells us how many comparisons we have to do on average. About 3 comparisons. How many did we do here? Well, we did one with the 100, we did one with the 102, and then we got it on the 3rd try. Hey, there you go. That's kind of close to the number here. And what would have been the worst case? The worst case would have been if it was bigger than 191. So in that case, we would have done one more comparison, I suppose, if we did this again to look at the 191 individually, and then we would have declared that it's not found. So as you can see, it's very close. Now in this case, there was 9 things. So technically the log of that is equal to 2 point something. I don't know, 2.2. 2 to what power is equal to 9 essentially. So, you know, I guess I can, cables here. I can plug it in here. 2 log to 9. Oh, I don't know why I put a 2 there. I meant the 3. I was like, huh? Yeah. So it'd be 3.16. I was close. That means that 2 to this power is equal to 9. 2 to the 3rd. It's obviously going to be, because we know 2 to the 3rd is equal to 8, and 2 to the 4th is equal to 16. So we know it's in between, but it's closer to the 3 than the 4. That's why I put a 3.2. That was not too bad actually. I was pretty close. So, anyways, in that case, why do we end up with 4? If I had asked you what 2 log 2.9 would have been, I would have expected a 4 answer for you. Why? Because when somebody tells you, this is kind of a bad example, but somebody tells you that for every 100 people, 9.5 are going to get the virus, the coronavirus, okay? You know, if they don't wear a face mask or something. If somebody tells you that, you know, what does it really mean, that 0.5 at the end? Well, you know, it's an average and so on. But if you only have 10 people, you know, and you have the statistics say 9.5, you're not going to have a situation where somebody's going to get half the virus, right? They're going to get it or they're not going to get it. So more than likely what could end up happening is that 10 people get it, because that 0.5 kind of, it just hits a person so it actually gets it, right? You may also just get 9 people that get it. But there's a possibility that that 9.5 means that 10 people actually end up getting it. So similarly here, when we say that the log to 9 is 3.1 something, it means that it can be on average up to 4, because it is possible that that 0.16 actually ends up making our 3 go all the way up to 4. As is the case in the real worst case scenario here of us looking for something bigger than 191, or smaller than the edge on the other side, which is 1, so a negative number or a 0. And so this is time complexity stuff, 302, don't worry about that. What you should worry about is understanding how this algorithm works. So let's go ahead and look at the code that this does it. All right, and for that, I'm just gonna open up, give you guys a link, and then we can talk about it rather than me just trying to code it, because there's no point. We can still copy the code and play with it, but that's the link. I posted it on the YouTube chat. And so if you go ahead and open up that link, and I'll go ahead and display it here. There we go. Geeks for Geeks is a great website when you're looking at learning algorithms of some sort. Actually for programming too, but I'd say the forte is the algorithm side. So when you're trying to learn like a specific sorting algorithm or a specific data structure, then they have code, examples, and sometimes even videos with the animations that really help you grasp the material. I'm sure they have, they have like a little animation on how to do binary search. As you can see here, kind of they do the color coding kind of how I did. They get the 16 there, 56, and then that, the 23. So I'm guessing they were looking for something between 23 and, yeah, so search for 23, yeah. So, yeah, and I'm pretty sure if you go to the bottom of this, yeah, they have a little video, and they're pretty short, compressed videos. Oh gosh, this is a 7-minute video. They're usually shorter than that. I'm surprised for such an algorithm they have such a long, because they have like Quicksort that's like 3 minutes long or something, and you'd be expecting that one to be the long one. But yeah, and so there's 2 versions of binary search. There's a recursive one and there's an iterative one. we're going to be looking at the iterative one because recursion requires me to actually teach you how recursion works, and that's 202 land. I might touch on it, maybe not. It's not something I'm scared of touching. So we can do it, but I'll leave it until the end after we talk about structs. And and we can even come back to the binary search and show you the recursive version of that. So anyways, for the iterative one, what that means is we're using loops. And essentially, what they are showing me here is and by the way, this is really cool. The website, it has it in different programming languages. So if you're curious what binary search looks like in Python, you can click there. And you can see that the code looks very similar, actually. Like if statements have an if, the while loop has the word while. You don't have semicolons, which is different. You don't have parentheses. You don't have curly brackets. But the code looks similar. Look at Java. Look at Java and C++. Those look almost identical. Like literally almost identical. Especially if you're just looking at the body of the function. The only difference being here that... what is the difference that I can see? The body of everything like here is identical between Java and C++, as you can see. But yeah, the only real difference is going to be in the way that the function call is made. Yeah, they're using length as the measurement, and then they have, I'm assuming that L and R must be, they're computing them in the function directly. But yeah, you can see that the code is very similar. So learning Java from C++ is a very easy thing to do once you know C++. You can see C# looks very similar too. And then, ooh, PHP, you know, variable, that looks a little bit weird because of the way variables are declared. But you can still see there's a while statement, there's if statement, there's an else statement, there's a return, and they use the word function instead of just, and Python uses the word define, whereas C++ doesn't have any of those. They just have the return type and the function name. So anyways, cool website, and also cool to see code in different languages, which is a nice way to actually, a way to pick up other languages as well. So anyways, let's look at this. They made it into a function. You don't have to, but of course it's what you would usually do, because then you can call the function at any time that you need to perform binary search, right? You don't have to code it every single time. So what do we need in a function for binary search? Well, we need to keep track of, I suppose, the size of the array, the actual array itself. We need a reference to that array, otherwise we can't do anything because it's in a function. And then we need to keep track of the left and the right boundaries. So remember how the left and the right in the beginning are the full array. But as we chop the array in half, we're only interested in certain sections of the array. So our left and right change accordingly. If you look back into what I drew here, in the beginning our left and right are 0 and 8. But when we chop the array in half, the left and the right now become 5 and 8. And when we chop it again, the left and right become 7 and 8. So as you can see, those are squished together until eventually they all point to the same thing, at which point you have nothing else to look for. So that's what left and right indicate, and we need to keep them as separate variables so that we can manipulate them as needed. So in this case, that's what L and R are. X is what we are looking for. So the X is the guess, or not the guess, but just what we're looking for. So if we're looking for the number 190, X would contain 190. That way we can compare what we're looking for with what is currently found there. And of course we can see that what we're looking for is bigger or smaller, so that we can decide which side of the array we need to look at next. So that brings us basically into the code itself. In the code itself here, it's essentially made, because this is the iterative version, into a big while loop. And at the end of the while loop, if we ever get to that situation with the end of the while loop, it means that we didn't find it. So, okay, the while loop is basically going to run until we crisscross the left and the right. What does that mean? Okay, in the start of this, again back to the Twitch chat, in the start of this, we started with a big array, and we have our left and the right basically pointing to the beginning and the end of the array, right? Like that. From there, the next thing we did was we have it pointing here and yet again here. From there, the next one, we had it pointing here and here, okay? If at that point we stopped because we found the 190. But if we had gone again, it's very possible, what would have happened here? We would have been looking at the 8, right? Just the index 8 alone. If we were looking for, let's say, 192, and we didn't find here with the 190, the next time we did a little computation here, the right and the left would both be pointing basically to 8, because that's all that you have left to look at. So then this would have been 8 minus 8 is 0, 0 divided by 2 is 0. So then 8 minus 0 is just 8. And so it's potentially here, we're looking at 8, our starting in our left is 8 and our right is 8. So we're both all pointing to the same spot in the array or vector. Also, it's possible that we could just completely flip it around. So the point where the left is a bigger number than the right, if you do it in certain ways, the algorithm. Either way, if left and right are pointing to the same spot, or they went beyond that, that is a sign that we've run out of items to look for. And when that happens, we want to stop searching. So that's why inside our while loop, the logical expression is we keep looping as long as the left and the right are either less than each other or equal. And if they're equal, that's basically the last time that we're going to look through something. Because what's going to happen later on is we'll have nothing else to do to search for at that point. It's going to be bigger and they're going to crisscross. Okay? So that's where this is coming from. Okay. So once we know that we have to loop through, what we need to do is we need to define what the index in the middle is. So what is that middle that where we're going to split the list, right? So in our case, we need to define that middle. So we need to pick the 4. How did we do that? With a little formula, right? That's how we pick the center. That's basically what they're doing here. I believe this is exactly the same as I had it. Yeah, it's the same. You have the right and the left. Yep, and then divided by 2, and then you have the left. Oh, they have a plus. I have a minus. So there is a difference there. So they're doing left plus, I'm doing left minus. Both work, as long as you're consistent. So there you go. Go ahead and do a plus if you would like. And so that's going to just get you the middle, or at least the middle that you're thinking is the middle. Again, why does it matter, plus and minus there? I mean, why does it not matter actually? Because if you have an odd number of items, it's easy to find the middle of something. But if you have an even number, you have to decide whether the middle is going to be to the left, to the right, because you can't have a perfect middle. So that's okay. This will just make you pick the other side. So actually, I had it as a plus and then it became a minus at some point. Looking at this, see that it was a plus and then it became a minus, but it still works. So yeah, let's stick with the plus so that we're consistent with the stuff. So if you go look at it later when you're studying, you don't panic because it's different numbers. So okay. Anyways, now that we found our middle, the first thing we want to do is we want to see if we got lucky, right? The way you do that is you simply compare the index at the middle with the value of x, which is what you're looking for. And if you got lucky, then it's great, you found it. So you return the index, which is what m is. Cool, but that's not always going to be the case, right? The other scenario is if you don't find it, you go to the next if statement here. And in this case, as you can see the comment, if what you're looking for is bigger than what is currently in the middle that you're looking at, so such as what happened to us, where we were looking at 190, where we were looking for 190, but we were looking at 100, and so 100 is less than 190. So in that case, we know that we got to look on the right side so we can ignore the left side. And so how do we actually ignore it? Well, we need to shift where the left is pointing to, because at the beginning the left is 0 and the right is the size of the array minus 1, which is the last index. But since we know that it's not on the left side, we want to shift this over here, or I guess because you're looking at it as a video, then I guess I'll do it this way. So you want to shift this over here like that. I can try at the end of class, yes. So yes, but yeah, so that's essentially what you want to do. So how do you do that? Well, you take your left and you're going to just increase up to the middle plus 1. So if the middle was at 4, you want to make your brand new left to be 5 because that's going to be after your middle, right? So from 0, you're going to do 0 is going to basically take 0 plus 4, which is just going to give you, oh, sorry, you're going to do 4 plus 1 because you don't want to look at the middle. You want to look at 1 after the middle. So essentially what we're saying is for the next passive numbers to check, we only want to check from 5 to 8. But right now, left is 0. How do we make from 0 to 5? Just go to the middle and then add 1 to it so that we don't add the middle again because we already checked the middle. So that's why you're seeing a plus 1 there. Here. Don't confuse this with an L. This is an L. This is a 1. The other scenario is if it's not bigger, then it must be smaller than. So that's if we were looking, for example, for 5. And we hit the middle here. The middle is, of course, 100. So we know that 5 is smaller than 100. In that case, we don't need to search the green side. We don't need to search the gray side. So we're going to do the opposite. We're going to move the right from 8 all the way down to 3. How do we do it to that? Take the middle and then subtract 1 from that, and that's going to be your new right. So 4 minus 1, 3. And that's essentially what happens here. N minus 1 right there. Okay? And so, yeah, I know this is like 4 lines of code, but they are a little bit tricky. You have to kind of, if you don't know the algorithm and you see this, you're like, wow, this is some black magic that's happening. But it's not. It's actually relatively straightforward once you actually sit down and look at it. So that's binary search for you, and it basically enables us to search things in log of n time, which is much faster because now think of big numbers, okay? N time for a million numbers is, and each one takes 1 second, is going to be a million seconds. But what is log 2 of a million? Well, let's search on Google and find out. Log 2 of 1 million. One more, like that. Okay. 20, if we round up. 20 comparisons that you have to look for. You have to look at 20 numbers before you find the number. Compared to the other method, which is just looking linearly, sequentially, you have to look at a million numbers potentially. Although on average, statistics tell us that on average, the number that we're looking for, if found, is going to be in the middle. So on average, you would only be looking at half of that. So instead of a million, you'd be looking at about 500,000. But still, 500,000 numbers to look at versus binary search, we just look at 20. 20, 500,000. 20, 500,000. That's a big difference. I don't care if it takes a nanosecond to look at that. You're still gonna do this way faster, and this can only go up. Let's go bigger than that. Let's push it to 1 billion now. So 3 more zeros. 30 comparisons for 1 billion numbers. 30 comparisons. You're only looking at 30 numbers for searching for a single number in 1 billion. I challenge you to look at 1 billion numbers and find the number you're looking for, whether it's found or not, in just 30 numbers that you look at. Without binary search, of course. Let's go to like the US deficit levels, trillions. What is it, like 15 trillion or 17 trillion, or I don't know how much it is. 44 comparisons instead of 17 trillion comparisons. Of course, like I said, on the average, you only look at about half of that because on average, if you're looking for a number, it's going to be in the middle. Okay, so instead of 17 trillion, you only have to do a easy 8.5 trillion comparisons versus 44 comparisons. I hope now you're starting to really see how big of a difference this can make the bigger the number gets. Yeah, sure, in the beginning, you're like, this looks so dumb because we're doing it on 10 numbers and we're doing so much work where we can just like look through it. Bam. Yeah, sure. 10 numbers. The comparison is not as important then. But as the numbers grow, you can see, yes, at start, if you're doing a car race and they're going, 100 meters, then if one car is much faster than the other one, you might still see the difference being really close between them. But now you go ahead and make a mile run, and now the faster car is really going to start showing that it's faster, and it's going to be a bigger difference, right? And then the bigger, now get other factors involved, but you get what I'm saying. The bigger the data, the more important the seconds matter. And in that sense, the more important your efficiency matters. Log of n time complexity is way, 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 way faster than linear complexity. And now we go into bubble sort land. Bubble sort takes n squared time, okay? What is n squared of this? So that's the other side of the equation, right? So sorting this data with bubble sort takes this time squared. 26 zeros. I don't even know what that number would be. That's an insanely big number of comparisons to sort the data using bubble sort. Fortunately, that's the situation that we end up facing. Searching is super fast now with binary search. But, the big but, it requires the data to be sorted. And if the data is not sorted, you can't take advantage of it. But sorting the data also takes time and effort. And if you use bubble sort, you're actually going to end up being slower because your bubble sort is going to take that many zeros comparisons. It's going to take a long time. As I said, people in 202 were doing some sorting in bubble sort of about 50,000 words, and it took about 5 minutes to do that. And the servers were like dying. They're literally freezing to death, and then they'd kick everybody out, and their sort would stop, and it was madness. So, is there faster way to sort? And the answer is yes, there is. And so that brings us to the next topic at hand, which are the other sorting algorithms that are out there. So we know that something like binary search allows us to search something very fast. And by the way, log of n, logarithmic time, is fast. But we can get faster than that. We can get to constant time using what's known as hash tables and hashing. Not always, not 100% for sure, guaranteed, but I'd say to the point where it's pretty much usable. That's how that's how password logins work. When you go in and log into Twitch or YouTube, imagine that YouTube has to use binary search and search through data to find whether your account exists and your password is correct. That's slow. Imagine doing it with linear search. Now that's not, you're going to be sitting there for a couple of hours waiting to log in. But when you press enter in that password and it's correct, you immediately get a response from the servers. It takes probably longer for you to communicate to the servers than the servers take to actually tell you whether your data is found or not. How do they do it so quickly? They use hashing. It's constant time. It's basically instant how they get that information back to you. And we want that because we're so used to basically absorbing data from the world, consuming media, that we don't like to wait. Because after all, we have a limited lifetime and limited time to do things. And we don't want to sit down and waiting like the days of dial-up, where you have to wait for a web page to load for 30 seconds or something. We don't want that, right? So speed is very, very important. And hashing allows you to do something in constant time. So that's going to be the best case, but we won't talk about that because that's 302 land. What I can talk to you about is how to sort things faster so you can take advantage of log of n time. And so right now, the best that we've achieved is potentially O(n) squared time, which is pretty bad because you saw the difference between n and log of n. But now imagine n and n squared, right? You're sorting 16 things. 16 squared is already a big number of comparisons to do, right? If you're doing 25 squared, that's 625, right? That's a lot of comparisons to do. That one I know. I don't know what 16 squared is, but I know what 25 squared is. So, are there other ways of doing it? Yes, there are, but I'm going to spoil you and tell you that there's a theoretical limit on how fast you can sort things. And that theoretical limit is actually n log n. So, n again being the size of the list. And that tells you the number of comparisons that you have to do, at least that many, in the worst case scenario. The best case scenario is, of course, I could give you a billion or a trillion numbers and tell you to sort them. And then you could look at them one time and be like, I'm done. I looked at them one time. It took me n time to look at them because I have to look at each one. And then I'm done. And I tell you, wow, you just looked at them and you were done? And they're like, yeah, you gave me a list that was already sorted. So, yeah, it's sorted. So I'm done. That can happen. That's, of course, your best case scenario. Your worst case scenario is going to vary depending on the algorithm. For example, the worst case scenario for bubble sort is if you give it a list in reverse order. If you try to sort something in reverse order with bubble sort, that's the most amount of swapping and bubbling up that it has to do. It's the worst case scenario. Some algorithms like bubble sort have a very clearly defined worst case scenario, which you really should avoid. Unfortunately, when you have such high amount of data, it's kind of hard to pick and choose, but you play the game of statistics. In statistics, statistics says that what are the odds that the list that you get is already sorted, whether it's ascending or descending order. Very low chance. More than likely, it has a nice little entropy where it's like very evenly distributed and mixed up. Then you can use your normal algorithms and kind of expect that average performance scenario. So in an average performance scenario, or in the worst case scenario of a sorting algorithm, you cannot do better than this. This is typically what you will see on average, and even in some algorithms in the worst case, and log n. What does that mean? If I got 10 items in my list that I got to sort, the lowest amount of comparisons that I can expect is going to be, and then of course, whenever I talk with logs in computer science, we're talking base 2. So that's going to be the least amount of comparisons that I can expect. What is this, of course? What is 2 log 10? That is going to be, again, something like 3.35. Again, we saw that to the 9 was 3.16, so maybe this is actually, maybe like 2.5. Something like that, maybe. So either way, we can round that up to 4 and then multiply times 10. So that gives us about 40 comparisons that we have to do between to sort the data using n log n. Now compared to something like bubble sort, where it's 10 squared, which is essentially 100 comparisons. Even with such a small list of 10, you can already see that there's a big difference between n squared and n log n and n squared. So n log n is still better than n squared. It's not ideal as n and log n algorithms, but again, there's mathematical proofs that tell us that we can't sort things faster than this. So if somebody tells you like, oh, I have a sorting algorithm that can sort things in n time or log n time, no, you can't. The math does not allow you to do something like that. It doesn't work that way. And if you want to know more about that proof, you will find out in 302. They should show you that proof on the board, hardcore and everything. It's not that actually hard. You can find it on Google. You can probably find it on my YouTube channel. If I was recording videos back then it would be there. So yeah. Okay. So cool. Which kind of algorithms can achieve such a speed? Well, let me go ahead and list most of the popular sorting algorithms, and I'll tell you what their speeds are. We have selection sort. We have insertion sort. We of course have our bubble sort, which we learned. And then, so these are all the kind of the lame ones. They take n squared time, not really fast. But then we get into the better ones. We got merge sort, we got quicksort, and then we got heap sort. These are in another league. They're the n log n time. Although technically quicksort is n squared, but there's a very, very special case where it's n squared. And outside of that case, it's n log n. And it's somewhat easy, not totally easy, but somewhat easy to avoid that special case. So it turns out that if you're just using a single sorting algorithm, quicksort is the fastest one of all of these. This is your go-to algorithm if you want to sort things quickly. However, it's not the fastest sorting algorithm out there, because the fastest sorting algorithm out there is actually a combination of 2 sorting algorithms out here. And that's going to be Quicksort. And it's what Python uses. And I do believe, I'll check it on Google in a minute here, that it's a combination of merge sort and selection sort. But, it could be insertion sort. I think it's selection sort, but let's go ahead and look it up. Quicksort. There's a link, and it says a hybrid stable. So it's stable. Remember stability that we were talking about the other day? Oh, merge sort and insertion sort. So it is insertion sort. Dang. Okay. I'm glad I checked it though. These two. That creates Quicksort. And Quicksort is actually what a lot of languages, such as Python and I do believe more than just Python. There's a couple used as the default sorting algorithm. So remember libraries, talking to my spiel about libraries and whatnot. Amongst the libraries that you have a sorting a library that you can just call to sort numbers, so you don't have to code these sorting algorithms by hand. So they must have implemented some sort of sort, and it's not black magic. They are pretty transparent about what that is. And in this case, for Python, they use Tim Peters developed this hybrid algorithm that mix and matches merge sort and insertion sort. I believe the way it works is when the data gets small enough, it's actually faster to run insertion sort on that small subset of data, and then you leave the merge sort for the big pieces of data. I believe it's something of that sort. Pun intended, I guess. N log n, time complexity. So the algorithm finds subsequences of the data that are already sorted and uses them to sort the remainder more efficiently. So essentially what it's doing is, most of the time these algorithms don't see the data beforehand. They just sort the data, ignoring any sort of pre-existing organization. Now, if it's a stable sorting algorithm, it helps you a little bit with that, but it can only go so far. What this merge sort is doing is it's trying to take advantage of the fact that most of the time, when you get data and you're actually sorting in the real world data, it's not just totally random. It's usually partially sorted and you're trying to add more data to it and sort that in, those kind of scenarios. Most of the time, that's kind of, the data is not 100% random. It's not just you just threw it in a bag and mixed it up and took it out. No, it's more of the time like you have some data that is partially sorted, but it got unsorted because you did some stuff to it, you want to sort it back in. So merge sort takes advantage of that by sort of doing these runs to kind of not mess up the order that exists, because it's more than likely something that is already kind of sorted. So it's pretty smart, actually, pretty cool. And I've always thought about trying to come up with a sorting algorithm that somehow uses machine learning into it, because I feel like that could be something useful. Because I mean, we have a lot of power in our heads to sort data fast, right? Machines can sort data faster than us only because they can do dumb things, but they can do them really fast and not get tired of doing them. Whereas we get tired of doing something that's not mentally stimulating. You know, if we were just given a bunch of cards to sort and it's a billion cards, pretty soon we're gonna just like shut our brains out because it's just the most boring thing ever. So can we kind of combine the power of the computers with sort of our ingenuity to sort things and the tech patterns? You know, could we do that? And so that's something that would be actually, I think, pretty cool to research. So anyways, okay, so from these, while I could show you all of them, I think the fastest one that I want to show you that you could probably understand is going to be merge sort. Quicksort is tricky. I can actually give you a very, very brief one, but I really would rather focus on merge sort. And heap sort, I don't think there's any hope in trying to go over that very quickly. But I do definitely have a video on YouTube about heaps, so you can check that out if you're curious. I don't know if I have YouTube's on Quick and Merge, because that was before we went on remote over last semester, so over the spring. So I don't know if those are up, but I think for heap there are. So yeah, the way Quicksort works, it's a recursive algorithm, although there is an iterative version known as lamp sort. And yet again, we don't really know recursion. So it's kind of tricky to teach you something recursive without telling you what recursion really is. But the way it works is you have your list of numbers. And this is, of course, numbers that are potentially in any order because they're not sorted. Otherwise, why would we be running a sorting algorithm on data that is, you know, not sorted? Or sorted already, I mean. And so the main idea behind Quicksort is to take your data and pick a pivot. And that pivot you can usually pick to be the last item on the list. And what you want to do is you want to create two sublists. Think kind of binary search style. And these sublists, you're going to split the data based on whether the data is bigger than the pivot or smaller than the pivot. And so usually you do this in place, but I'm not going to do it in place so that you can understand it better. What you do is, 3 is your pivot. So anything bigger than 3, I'm going to put in this sublist. Anything smaller than 3, I'm going to put in this sublist. And ideally, these will be the same size. Realistically, that's not going to be the case. It's very possible that one size is completely empty and one is full, such is the case if the pivot is the biggest or smallest element. The scenario where they're going to be even is if I had the median value. I believe it was called median. Yes, I believe, no. Yeah, median is the middle number, or yeah, I think it's median. I don't know, I can't remember the math term for it, but it's not technically the average because that doesn't really tell us, but you want the one that's in the complete middle of this. So anyways, 3, with duplicates, just pick on one side, put them on the left side, why not? 1 is also small, 2 is small, 9 is bigger, 5 is bigger, and 10 is bigger. So that actually turned out pretty well there. I did not expect that to be the case, but it did. It actually split them very nicely into halves. So after you do that, you have the 3 left over, okay? And so you know that the 3 is in the right spot at this point of the list. Because even though these are out of order, you know that there has to be 3 numbers before the 3. And I know there's another 3 there, but that doesn't matter. And these 3 have to go after the 3. So what do you do then? The exact same thing. This is literally all there's to it. Now you just got to repeat this over and over again. Rinse and repeat until you're done. So let's pick a pivot again on this side. Let's do this side first. We got this as our pivot. And so now we're going to create again 2 lists. And we got our pivot in the middle. And we're going to put them based on that. So the 3 is bigger and the 1 is smaller. So bam, we got this now. So now what we have is 1, 2, 3, 3. As you can see, it's sorted. On the other side, we still got to do this. So let's go ahead and pick our pivot. 10 is going to be our pivot. So far, we've been pretty lucky with the splitting of the data. It's split pretty evenly. Now we're going to see a situation where the data doesn't split very evenly, and this is technically the worst case of this sort of partition. Again, we're splitting it based on the pivot. Pivot's going to be basically in the middle of our 2 lists. Of course, this one's quite simple because yet again, there's only 2 items there. So the 9 is smaller and the 5 is smaller. So you put 9 and 5. And the 10 is on the right side is empty. So again, why is this the worst case scenario? Because one of the partitions has 2 numbers in it and the other one has nothing in it. So pretty inefficient because this iteration we only sort of sorted 1 element. This is on the bubble sort tier, which is why if we kept doing this, it's every time we try to partition, we picked one side, we picked a pivot that was always making everything go to one side, we get into bubble sort land, which is why Quicksort can degrade itself to n squared, but it's very rare unless your data is intentionally maliciously organized that it can happen like that, or you're just horrible at picking the pivot. So anyways, from there, we're going to do the same thing on the 9 and the 5, picking the 5 as a pivot because it's the last element, and we're just always going to pick that. We're going to be consistent. I'm skipping ahead here. Okay, so the 9 goes on this side, and that's it. There's nothing else. So now, this is technically also the worst case, but it's not really because there's only 2 elements and there's no other better case, so whatever. But we're done. At this point, we got the 5, the 9, and the 10 in the right order. And we also have the 1, 2, 3, 3 in the right order. So essentially, this becomes that. And we have sorted our list. If you're like, what just happened? That's okay. Oh, damn. I never saw that until now. Could you give us a quick reminder of what stable means? So stable means that if you have duplicate keys, they don't swap. They don't change order. So if you're sorting in bubble sort and you see 2 3s, the 3 on the left side is always going to be the 3 on the left side. Of course, if you're just sorting numbers, you don't care technically, right? But imagine that those numbers were just part of the data that you're sorting by. The example I gave is you're sorting a bunch of ships and you're sorting them by weight. But you may have two ships that have the same weight, but you know they're different. So how you sort them, they may end up mixed order. You may want to keep them in that same order so that this ship and this shows up before this ship, even though they both weigh the same. And if you feed it that way to the sorting algorithm, you expect it to stay in that order because these two are the same weights. So that's what stability means. Quicksort is not a stable algorithm. And case in point, in this scenario, it actually maintained that stability, but that's not always the case. In fact, I'm going to show you now how to do the in-place version of Quicksort. But again, if I just went over this and it just went over your head, don't feel bad. This is a 302 subject that will get covered in detail there. This is just an introduction into it. I'm not going to make you code Quicksort on a test. All right? So this is just for you to start to understand, because it's important that we kind of get you going on these algorithms early on in your computer science career. So let's go ahead and redo this the way it actually would get done, because this is all very nice and pretty looking, but computers can't. I mean, you can do arrows, but you know, you have to be more technical. So let's do what's known as in place, which is how the real algorithm works. So with a real algorithm, you're not going to have this little sub list where you can copy and paste things. You have to sort of sort in place. So what ends up happening is, and it's been a while since I've done this, 2 months, so hopefully I remember it still. But you start out with there's two ways actually to do this, two completely different ways. I remember that now, to the point where I showed one way in class and then I show a video in class for the second system. Yeah. So I'm going to do the way that I personally like, and I think is a better way, but there's two ways. So if you Google this later and you find a completely different way of doing this partitioning scheme, it's okay. And they both have names. And I can look that up. It's on my Canvas for 302. Let's see if I can very quickly pull up the naming convention of these two different partitioning systems. Quicksort versus Mergesort. No, Quicksort reference. I don't see a name to them, but I'll post a link to the other method. Yeah, this is a YouTube link. That video, there is one mistake in the video, I think, that that I don't quite like. Not mistake, but something kind of inefficient that he does. But overall, it's pretty short and nice. That's one way of doing Quicksort. And then the other way is what I'm about to show you now. Again, these have names, but oh, here we go. So this is known as Horse partitioning scheme, and the other one is known as Lomuto's partitioning scheme. Yeah, there we go. So Lomuto is the one in that video. Let me write that guy's name here, since it's quite interestingly complicated. That's Lomuto's partitioning scheme, the one in the video. And the one I'm about to show you is known as Horse partitioning scheme. Okay, so different people. I do believe Horse is in general the better one, which is the one that I know, because it's faster actually. Like it legitimately is faster, so it's better. So might as well learn the faster one, right? Why learn the slower one? So what you do is you got a left and a right sort of indices that they're kind of pointing, right? Kind of like in binary search. So you have your left and the right. And what you're gonna do is you are going to swap the left and the right if they violate the pivot property here, where in this case neither of them do, because the left is smaller than the pivot, or equal to in this case, and the right is bigger than the pivot or equal to. So what do? You just keep checking. So you slide the left to the next number. It turns out that the 1 is also less than the pivot, so you're okay. You keep checking. The 2 is less than the pivot, so you're okay. You keep checking. The 9 is bigger than the pivot. So in that case, now you gotta swap the 9 with something that the pivot can swap with. So you start moving the right. The 10 is bigger, so you don't do anything. The right is bigger. Oh, sorry, the 5 is bigger, so you don't do anything. At this point, both of them are pointing to the same thing. That is a sign that you're done doing the partitioning, at which point you're gonna swap the location of the pivot with the location of the 9. So you use your little swap function, and you put the pivot there, and you put the 9 there. Okay? More importantly, at this point, you're going to feed to your partition function this subset and this subset of the array. Okay? And so you're going to call that with left and right being 0 through potentially 3. And then similarly how, this is the recursive part, but similarly how in binary search you rerun the algorithm with a different left and right, you're going to rerun this algorithm with two sections actually. One for the left partition and one for the right partition. So you would basically, it's like doing binary search on both sides all the time. In fact, binary search and Quicksort are really, they go hand in hand, by the way. Okay, so from there now we got 3, 1, 2, and we got 5, 10, and 9. And so what we're going to be doing with 3, 1, and 2 now is the same thing that we did before. So we're going to pick this as a pivot. And it really doesn't matter at this point whether I do the left or the right side first. Left just sounds better. But the beauty of this is that you could actually make two separate computers do this. One does the left and one does the right, assuming that these are big lists, of course. And that is basically one way that you can speed this up. Divide and conquer can apply also to dividing your work between multiple people, or in the case of computers, multiple computers. Okay, so we have a left and the right here again. In this case, this is left and this is right. The left is bigger than this, so we want to swap it with something. The one is smaller than that, so that actually means that we can swap it with that. So we're going to go ahead and do that. So the 1 and the 3 get swapped. And then technically the left moves up like that. Okay? And so now, yet again, we have the left and the right pointing to the same thing, at which point that means we swap the pivot with that. You only swap it if the number on the left and right is bigger than the pivot. Otherwise, you don't swap. I do believe we'll see a scenario with that. But so you basically are going to swap the 3 and the 2. Okay? At that point, we are finished with that. And technically, if you're not doing this the most efficient way, there are some ways to make this a little bit more efficient. You would send this partition to the, like again, to do another pass per se. At which case you would basically have left and right already pointing to the same thing, because you would make basically this your pivot. At which point, that would be a scenario where you would see that the 1 is smaller than the pivot, so nothing would get swapped. So then you'd be done. So essentially nothing is going to happen because the list was sorted, but technically it does, right? Okay, so now we're done with this side, so we can move on, work on the other side here, the 5, 10, and 9, or another computer could have been working on it, as I said. So what were they doing? Well, they went ahead and picked the 9 as a pivot. And then, and by the way, notice that every time you run this, the pivot is in the right spot of the list, as I said before, okay? So we get the 9 and we got our left and the right. Let me get rid of this one so you don't get confused. And let me make this gray so you're not looking at this anymore. So left and right, 5 is less than 9, 10 is bigger than 9, so that's all good, which means that the left can move up 1 spot. Yet again, now left and right are pointing to the same element. That is a sign that you're done. Now you just gotta swap the pivot if necessary. In this case, the left and right is bigger than the pivot, so you do want to swap it. So yeah, we got to see that happen. Okay, and then like I said, technically at this point, even though the whole thing is sorted, we don't quite know that for sure, so we got to do one more pass on the 5 and the 9, where then basically we pick the 9 to be our pivot. And then the left and the right, though, end up pointing to the same spot because there's only one spot that they can both point to. So that kind of automatically tells us that we're done. And then we look at 5 and 9. 5 is smaller than pivot, so we don't swap it. So then we're done, of course. At that point, we don't do another call because we can check that we only have one element left to look at, which means that it's not going to move. And so there you go. This seems very complicated, but it's so much faster than Bubblesort. And if you want to look at what code for this looks like, actually, I can open up Geeks for Geeks Quicksort. Probably the same link that I have here. Yeah. Oh, this is a comparison of both methods. This is Lomudo's method, which is actually easier to code, but slower. And Horace's method, Whoa, is this an iterative version of that? No, because it's recursive. So this is recursive, and yet again, we don't really know how recursion works too well or at all, actually. But you can kind of see the code, and is this C++? What are you using to do? Oh, it's a do-while loop. Okay. Why are you using do-while loop? I don't know. But anyways, here's us picking the pivot. In this case, I think they're picking the first element as the pivot. No, they said last element. Why is it called low? I don't know, but I guess they do pick the last element as the pivot, as I did. And then they go ahead and set up their left and rights. And then they basically are walking through the array on the left side. And then on the right side, if there's something they have to swap with. And eventually, once they find something, they swap it. Otherwise, if the left and the right, which they're using as INJ, if they both cross each other or point to the same spot, that means that you're done at that point. Hopefully they don't cross. In this case, they should, if you do it the way I showed you, they should always just point to the same spot. You should never run into a situation where they crisscross. That's kind of scary, so beware. And then you don't know, the main function here is basically you're calling quicksort on both left and the right partitions because you got to sort both halves. So that's why you're seeing two function calls here. Like I said, you can send them to different computers to sort the left and the right. And that actually happens every time you split it, because in this case, when we split it, because it was such a small data, we only, well, at the first time we split it into two, but from there we basically split it into one piece each. But if we had bigger data, you'd see that it go into two here, two here, two here, two here, and so on. It'd be like a big tree. And yeah, that's a quick overview of Quicksort. I know I said I would show you Mergesort, but I ended up showing you Quicksort, so that's okay. We still have a little bit of time. Instead of talking about structs, let me show you Mergesort. Mergesort is so much easier to understand, but it actually, I feel like it's sometimes a little bit harder code. Especially if you're using an array version of that versus like a linked list version of that. Let's use the same data. Why not? Mergesort, as the name implies, is all about merging, basically. It's like you take it apart and then you put it together carefully so that you sort the thing. That failed. Okay. So here we got our list. I feel like we lost a number. 2, 4, 6, 7. I don't know. Let's just add another number in there. Actually, no. Let's leave it like that. To show you what happens when you have an odd number of things here. The way Mergesort works is you're going to basically break the thing apart into tiny little individual elements and then slowly put it back together. So this is going to look like a little diamond shape. What does that mean? Split this in half. How do you find the half? Same way as binary search. Just take the left and the right, you know, subtract, divide by 2, add that, blah, blah, blah. You're good to go. Same idea. So when you find a half, you split this into two separate arrays. Obviously here, yet again, you know, this is not an, it's just an odd number, which is why I actually kind of like that, to show you that it doesn't have to be split in exact half. However, in this case, unlike Quicksort or binary search, you do want to take that middle spot. You don't want to leave it there. You actually want to put it on one of the partitions. Whereas with Quicksort, the pivot is kind of its own thing. And with binary search, you look at the middle, but then you ignore it when you're doing the partitions because you already checked it. Here, you do want to put it on one of the sides. So either the left or the right. Doesn't matter. Just be consistent. Although I think it's not as important to be consistent on this one. I mean, you should be in general, but it's not as critical. Okay, what do we do next? We split it again. Just keep splitting this into smaller little arrays. Here again, you run into the situation, but we're being consistent, which means that the left side is bigger than the right. So I guess we'll go with that. Okay, we got to do one more split layer here. 3, 1, 2, 9, 5, 10, and then technically 3, and then there's nothing on that side. Okay, so I guess we can erase that. All right, we split everything. I know that seems like a lot of work, but it's kind of part of the process. That's the easy side, actually. So we split the entire array into individual elements. Now comes the merge in Mergesort. So now we gotta merge it back together. So how do we do that? Again, this is a beautiful algorithm to actually parallelize and have multiple computers running on it to speed it up. Because each of these can work individually until you got to put them back together. So, but again, we're just one computer, so we're going to basically just go left to right. Let me actually get rid of this because it's gone off on the way. So let's start with the 3 and the 3. Let's merge those together. How do we merge it together? Well, when we have individual elements like this, just look at both of them, see which one's bigger, and if you're doing ascending order, then put the smaller one on the left and the bigger one on the right. Easy as that. You can use a bubble sort logic for this. Same here. Are these all already sorted or something? No, I see. Okay. And here we have only one thing, so in that case, it just stays as one thing. Okay, that wasn't very exciting or special, but it's going to get a bit more interesting here in the next step. What do we do again? Merge. But this time we're merging two things that are potentially more than one element. How do we do that? All right, so this is where the fun begins. It's not that hard. It's very easy to understand. It's a little harder to implement, like I said. What you do is you keep two little pointers or indices to the beginning of each of your partitions or sublists. And what you do is you're going to work your way to those to progress them all the way to the end. So I guess the video is this way. So progress them this way, okay? So what you want is this little arrow to go through the 1, then the 3, and then go here, which means it's done. And what you do is all you're ever going to be looking at is two numbers. And that is what the arrows are pointing to. And at the beginning, they're going to be pointing to the first element of each of the sublists, which are usually about the same size, but they could be a little bit different as you see on the example with the 3. So in that case, what we're going to do is we're going to look at the 1 and the 2, and we're going to pick the smallest one of those and add it to our merged list here. So we add the 1 because it's smaller than 2. Next, we're going to move the arrow to the next number in that sublist. The 2 stays in there because we haven't looked at the 2 yet. So next, we're going to look at the two numbers that the arrows are pointing to, the 3 and the 2. We pick the smallest one of those. Now the 2 is the smallest one. So we add that to our new list here, and we move the arrow to the next spot. Now, we're looking at the 3 and the 9. 3 is smaller, so we're going to go ahead and add the 3 to our sublist, and we're going to move the arrow to the next spot. But in this case, it has moved outside of the list, so it's out of bounds per se. That is a sign that we are done with one of the list. At that point, because of how Mergesort works, we can just append the remainder of the list, of the other one. Of course, there's only one thing in this one, but I'm saying if there was a lot of things here, we can guarantee that those things are already sorted, so we can just literally grab this and put it there. We can append it like that. So, yes, basically that's what you do, okay? We're gonna do the same thing over here. We start out with a little arrows pointing at the 5 and the 3. Oh, this is a beautiful one because you get to see that. The 3 is smaller than the 5, so you add it in. At which point, come on, arrow. Yeah, well, there goes that. There we go. The arrow points out of bounds. Because we finished one of the sublists, the other sublist doesn't even need to be looked at. We can just append it. So literally append it. So take our list here and just append it there. Because we guarantee that it's sorted. That's just one of the beauties of the algorithm. Finally, we're doing our last merge. Of course, this could be way bigger, more merges and more splits if it's a bigger data set, but it's the same system. Okay, so we again start with little arrows at the 1 and the 3. In this case, the 1 is smaller, so we can put in the 1. Move the arrow to the next one. The 2 is smaller than the 3, so we put the 2. Move the arrow to the next one. In this scenario, you got 2 3s. You got to be careful about this. Always go with the one on the left side first, because Mergesort is a stable sorting algorithm as long as you don't screw this up. If you screw this up, then it's no longer stable. Quicksort is not stable. Mergesort is. In fact, I actually never pointed that out. With this quicksort that we did here, we actually ended up flipping, probably. Oh no, we actually got, I think we got, did we get lucky with these numbers here? We did. We got lucky with that specific combination of numbers where the 3s didn't get flipped. But it's possible that they can get flipped as you're doing the partitioning. Whereas here, you guarantee that those 3s will not flip as long as when you're doing this merging, you don't screw that up. When you have duplicates, take the left one first. So we're going to take this 3 over here and copy it down. Okay, and then we can move our arrow to the next number, and then of course the 3 on that side is smaller, so we can copy that 3 down. As long as you do that, this is a stable sorting algorithm. I guess that's one of the pros of Mergesort versus Quicksort. Again, any unstable algorithm can be made stable by just adding an additional key to when you're sorting. All right, 9 and 5. So 5 is smaller, so we can go ahead and do that. Now we got 9 and 10. 9 is smaller, so you can go ahead and do that. At which point, this is out of bounds, so we can copy the remainder of this list, which is just a 10. And there you go. We have now successfully sorted this in n log n time using Mergesort. Chat, which one do you like more, Merge or Quicksort? Curious. They're both really good. Pros and cons. Merge is stable, Quicksort is not. Merge is very nice to parallelize, which means you can have multiple computers running it, which is one of the ways that we can speed things up. Quicksort is faster than Mergesort on its own, though. But again, it's harder to parallelize parts of Quicksort. So you'll ask like Quick more. Interesting. I like Mergesort personally more, but that's okay. And I have used Mergesort in the past more often, so I guess that could bias me. It's just Mergesort seems very elegant because you just split things up and put it back together. And it's also easier to see why this is log of n, because you see how things are split by halves. And so that's where that logarithmic part comes in. But then merging together takes the n part. So it's very easy to see why this is an n log n algorithm. Whereas with Quicksort, it's a little bit harder to analyze that in terms of time complexity. But yeah, they're both very cool. And yeah, I definitely think that understanding Mergesort is a lot easier than understanding Quicksort, because the partitioning and the pivot stuff really confuse people. Like when I go in 302, a lot of people have a hard time sometimes with the whole partitioning stuff and coding Quicksort. You guys are actually lucky that I go over the code, because I don't go over code in 302. We just go over the theoretical, and then we make the homework be the code. So and people were like, "Oh, we want to see the code." I'm like, "Yeah, if I show you the code, then what's the point? You know, you're just gonna copy and paste the code from the internet." So yeah. So anyways, that's the lecture for today. Actually, we got all that I really wanted to. So now you have a more serious understanding of sorting. And while I don't expect you guys to go home. Well, you're already home, right? But I don't expect you guys to just sit down and start coding Quicksort or Mergesort. It's still nice to look at them and understand them, because now you know that if you need to sort something, you can call a library that uses Quicksort, and you know that's going to be way faster than BubbleSort, right? So at least you know that much. And then at some point you will pass the trial of learning Quicksort and coding it on by hand on a test when you get to that point if you're a CS major. But yes, Mergesort, I feel like it's a little bit harder to code if you're not doing a linked list method, if you're using arrays, because it's just hard to keep track of like the lists, the left and the right, and it's a little bit messy. Quicksort is just a lot cleaner, even though people get scared of Quicksort because it's recursive. I'll throw in recursive at some point, maybe Friday, and if not on Monday. It's another thing that actually people get scared about. Recursion and pointers are the things that people get scared about the most in programming. So yeah. But anyways, for now, if you guys went ahead and attended class, send me a message on Discord so that we can give you those 10 points extra credit, all right? So yes, this will be on YouTube, so you guys will be fine, all right? So anyways, are there any additional questions? All right then. Well, then I'll see you guys tomorrow. Oh, shoot, that's the storm stuff. That's right. Yeah, I forgot about that. Okay, so let's talk about the assignment then. So this is an assignment that I have done before, and I really liked it, which is why I threw it in again. And so, what was the question again that you guys had? You want to see for print and clearing and updating text in the terminal. Yes. Okay. So if we go ahead and look at the assignment page, let me go ahead and pull that up. I have some code here. Here we go. So if you want to erase output, you can do this little function that will, not function, but piece of code, that it will basically delete your output. But there's an easier, cleaner way of doing this, and that's just using system clear. So if you want me to show you that, you can call something like system clear, I believe it is. Like that. And then I believe you need to have stdio.h included in that. And if you run that command, it will remove all of the text from there. So you have a clean slate. So like every time you print out, you can call that command to clean out. And then of course it will clean everything. So then you got to print out the little title of the game again. So that was that. And then the other part that people were asking was, how do we get the storm to go around the center? Well, you got to pick a center. And then when you pick a center, you got to do some math for that. So first of all, remember, where's your 0, 0? That's up here, right? And then potentially here, you know, if your X is your horizontals, then this could be like, what is it, 50, 0? I don't know. I don't remember how big I told you guys to make this, how wide. Then this could be 0, 20 or whatever, 0, 30, and then this would be 50, 20. So if you have to RNG pick the center, right? And you can use rand for that. You can look at the video from yesterday or yeah, the one yesterday where we did rand. So you can use modules for that. Just use the sizes as your ranges. So anyways, suppose you pick a spot here, and the spot you pick is maybe let's say it's 5, 20. That's kind of around there. But okay. So if you pick that as a spot, you want the storm to be closing in on that spot. So what you need to figure out is which way the storm needs to grow. And so if you want the storm has to go in 4 directions, right? Towards the center. So if you need the storm to move this way, what you need to do is you need to add +1 to your X values. Whereas if you want it to go this way, you need to subtract 1. Over here, if you want it to go down, this may be counterintuitive, but you have to add 1 to it. And if you want to go up, you have to subtract 1 to it. So you got to make sure that you get those things right. Does that kind of answer what you were asking? Cool. And if not, then just let me know on Discord and I can show you. So, all right then. Well then, thanks for hanging in there with the whole situation with switching over from Twitch. But, you know, it is what it is. I'm actually going to test trying to go on Twitch later. So if you see me around, if you get a notification of me going online, it's just me testing it. Doesn't mean that there's class happening. Class will happen tomorrow at a regular time. If Twitch fails again, we'll use YouTube. And as a worst case, we also have WebEx. So life will find a way, lecture will find a way. But for now, thanks for coming by. You know, stay safe out there, and I'll see you guys tomorrow. Bye.